No, you come. That's why I was asking. You guys know each other before. That's what he just said. Yeah, you know that. Same supervisor. So that's why you know. That's interesting. Well, that's good though. So I think that gives you some company when you like come out and because you guys don't come and eat in that other guest house. You know, I think he alone comes. So I was wondering, you know, then he said that you guys saw this other, but probably you guys eat in that canteen. It was closed on Sunday? Is it because of the play or is it because of Sundays they closed?
Sunday they closed.
Was it?
They said they closed. Now if some other festival or more students are there or something.
Yeah, they'll keep it open. So what did you guys do
So
then?
we think lunch we ordered.
From where? Okay, so they're bringing it. That's not bad. Yeah. But you know, you have also an option in the other guest house there. Yeah, they have a place to eat, and I think, as I said, it's not that far. Although, I don't know, I know one day is okay.
Sir, we went to the other day, we went to the guest house of South
yeah.
just to a lot of nice garden is there.
Right, no, but that is nice. The front is nice. But it's just the food. Well, I think.
So actually, I have been here
Before. Okay.
So I tried to avoid this also.
But I don't know I had a chai in that hall, like that canteen. I don't know. I didn't think particularly it's better than the guest house. Guest house, chai and coffee and all they're pretty good. You know. The only thing is they repeat more often. There's no option. Yeah, the same kind of food. Right. No, but that's the best thing I think you were talking about. Yeah. That's the best thing. Okay, I think we may start. I know there are a few more people. I don't know whether they'll come on time. So what I do today is I would show the optimal control using critique. Remember adaptive critique. So there are some videos I can't show when they're recording, so I kind of deleted them out. So the ones I can show, this is one, and then the other one is the event trigger part. I can show you maybe I won't have time today to cover it, but I would be able to cover it tomorrow. So you can go back on that video. So remember, we looked at, so far, everything is optimal control, right? Optimal control, and the way we designed the optimal control, if it's a linear system, it's basically Q-learning, right? Q-learning approach. And if it's a nonlinear system, we are using neural networks. And the way we designed, there are a lot of different ways using neural networks you can design it. You could have even one neural network, okay? And that's a critique. So what you do is, if you remember, the actor, you don't have to have a neural network. Critique provides the value function, B. You take partial V over partial X of K plus 1, and as long as you have G, you can come up with the actor, if you remember that, right? So a lot of times people want to have single neural network rather than two because of computations. And if you know Pati, Dr. Pati from Radhakant Pati from IAC Bangalore, they usually talk about a single network critique, and that's what it is. His PhD work was using single, is nothing different, but I'm just saying that for that you need to have the G. But if you remember, you can use two neural networks, one to approximate Q, other one to approximate G, but you still need G that control coefficient matrix because that's required, you know. Otherwise you can tune the actor neural network. Remember that. So that's why what we did was, if you remember, we added an observer or identifier. Exactly. We have to have that. So that helps you to get the G, which is a G hat. Then you use with two neural networks and you are able to do that. Okay? So either you use an identifier if your states are measurable, or you can also use an observer. Now that's a new thing that came out in last 10 years. Typically observer requires the dynamics, okay, of the system. So if you look at what we covered that the observer also can relax the dynamics and uses the output basically to tune to estimate the state of the system. So this is it's kind of an identifier, you see. So I think that's something you need to realize that. So what I'm going to show you is a comparison of a video which was done in 2012 of an adaptive critique optimal controller and a stabilizing controller. Stabilizing controller doesn't use optimality. So you want to compare and in a real hardware. Because we know in simulation I showed you and we always think that optimal gets better and you know it's an additional computation and all. But the fundamental question is, does it behave the same way on the hardware? Okay? And I think that's one thing. The other thing is, we'll see there is an obstacle avoidance. I thought I would show you. There was somebody was asking me, there's a lot of work I have done, but this has a little obstacle avoidance. There's a little bit AI in there. Basically, you know, it detects the obstacle and then it decides how to avoid it, but then you will see that there's another robot in the front. So if he tries to move to the right, then you have another robot. So basically, just like a human, that robot slows down and waits till that other robot passes by, just like a human. Remember, when you are trying to bypass somebody, then you see something going on, what do? You slow down, let him pass, and then you go back. So there are things like that, one of the things that you will see, and this is for formation control. So I have, so here we have one leader we call, and there is a follower. And the purpose of the follower, you just follow the leader. If the leader makes a right turn, you also make a right turn. And the goal is to maintain some distance between the leader and some bearing, some angle, okay? So this is a very typical problem, like in automated highways systems, you know, where you don't have to drive the car. Once you reach the lane, you can put it on the cruise, as I said, adaptive cruise, and everything, the system would take care of it. Because it looks at what is in front, and then the car in the front slows down, your car also slows down. You know what I mean? So there's a lot of work has happened in autonomous vehicles for transportation systems. Okay? So this was one of the works that we have done. So you can see that in this one there are, for the leader, there are, and this is for the follower, there are two plots. These are hardware results. One is the blue, which is using, both use neural network. But the blue one is mainly a stabilizing control. There is no optimality in there. Okay? And the red is basically the optimal controller. So you can see the optimal controller has given you lower cost than the stabilizing controller. Okay? And you can see that the weights are getting stable. And here the values, the average value. Leader, you can see 126. Okay? And if it is a stabilizing controller, it's 192. The total cost. And for the follower, it's here is 829. Whereas here, it's at 2,000 something. So what you're doing is there are no units. You're taking a quadratic cost, the quadratic cost of the error C transpose QE plus U transpose RU. The same values of Q and R. Only thing that's changing is the error and the input. You see? So you're comparing the two, okay? So let me play the video. Let's see if it plays. Oh, it's not playing, so it's. I didn't realize I should have brought my laptop. Maybe I'll bring it tomorrow. So it should play, the video. I don't know why it's not playing. I didn't realize that. I forgot that's a problem. Would be a problem. So this also, I don't think it plays. Yeah, it's not playing. So in this case, see that the publications essentially cite this is a drone in the lab, and one of the things we have done is, which I'm going to cover in the last chapter, mainly event triggered. So I'm going to show you as you stretch the sampling interval what happens. And in this case, you will see there are 4 videos. As you stretch it, then it doesn't become stable because essentially the feedback gets delayed. So there's only so much you can stretch. Anything beyond that, it doesn't, So there are a bunch of 4 videos there. And there's a paper that came out in 2019, I think transactions and automatic control. Okay. So basically, the hybrid, what I want to show you is, the hybrid means, remember I told you, I explained to you, in the optimal state, we are only updating the weights once a sampling interval, right? Remember that? But then the policy iteration paper I sent you, right? I already sent it. The paper that I told you, that was a policy iteration paper. So the policy iteration basically is you solve it using purely numerical methods where you're holding the time at the sampling instant and you iterate it for a very long time. Once it converges, you stop and then you update the time. But in practice, the sampling interval is fixed. So the problem comes in is how many iterations, and if you have many iterations, you can't complete it within the sampling interval. Things will blow up. So here, we came up with the hybrid, where you take a few iterations based on your sampling interval, the duration, what that's left over, and you're also updating it once a sampling interval. And then the modified hybrid, you see that basically uses the history. The hybrid doesn't use the history, whereas the modified hybrid uses the history. You see that? So what happens is, you can see the Bellman error. The modified hybrid converges much faster than the hybrid method. Okay? So, but now, you look at this one. Somebody asked me, what's the difference? Like time difference, the one that we are doing. So you see that I kind of plotted a ratio, hybrid versus temporal difference. Okay? So what it shows is, if both are equal, then then the value should be equal to hybrid, or temporal difference should be 1. But here the ratio is less than 1, right? So that means that hybrid is doing much better than the temporal difference. So this is another way to look at it. So that and we have plotted we have a lot of papers that shows how hybrid is a lot better than the one that you guys are doing, temporal difference, okay? So this video that I thought I could run it, but I think on this laptop, I may bring it tomorrow or something, or Wednesday. So in this laptop, it's not running. So this laptop, basically, this is mainly a regular optimal controller without hybrid. But if you added the hybrid, it does much better job. Okay? It has got the obstacle avoidance. Maybe in the afternoon when I come, I can also bring or maybe, because if you are going for the tour, I won't bring it today. Maybe I'll do it tomorrow. So that's what I thought. Okay? So here, the hardware implementation, I will tell you, it's a 8086 processor. 8086 processor was designed when I was an undergraduate student. It was a 16-bit, very limited memory, and we had 3 neural networks we are implemented. One is the observer neural network or identifier, because the mobile robot, remember I said that it's a non-hologramic. And you will see that, so I don't know whether I thought I had another slide, but I don't think it's there here. It's here. Okay, so, and it goes around in a circle. And the follower also goes around, nicely shows. And one for the observer. Observer estimates the states of the system. You don't have sensor to measure all the states. So we have a sensor that can measure the distance from the leader. And we have a sensor that measures the bearing angle. That's all. The position and velocities are all estimated from the observer. The second neural network is critique neural network, which is approximating the cost function. And then you have the third neural network, which approximates the action. So all the three, remember that software that I intro to oral, the Travis paper, that's exactly the implementation. The only difference is in that paper, Travis paper, there is no observer in the simulation. Here we need an observer because we are not measuring all the states of the system. So the idea from that paper is implemented in the hardware. So I couldn't play, I didn't realize it. So I will bring my laptop and then I will play that. Okay? So any questions? And then this one, again, I will try to play this. This particular video is mainly, it does is event triggered sampling, and we're going to talk about it in this chapter, the last chapter, lectures 9 and 10. Okay? So I'm going to switch it to that chapter. So any questions here on the hardware implementation? So that paper, there was a paper that was published in IEEE Transactions on Control System Technology. Okay? And that paper essentially has the hardware results. And it was published, I think, 2012, I think, Transactions on Control System Technology. And it talks about all this stuff in there. And with reduced information, it basically the exchange of information is reduced. Because you're using wireless network, you may not be able to transmit a whole lot of data from the leader to the follower and stuff like that. Okay? So it's a really nice videos, these are, and I didn't realize that I can do this. I just copied the video, but I didn't realize it. This is the other reason why. Okay? Any other questions?
Sir, probably in the previous slide there was a table. Yes. So what is this UNN?
So the difference between the two is the UNN is mainly the stabilizing controller without any optimality, the control input, whereas that other one, the first column was the optimal. So there are other slides, this particular deck deleted all of them, that's why you don't see them, So this particular one was, the first column was optimal control. Okay? And that's the total cost. Total cost, the first row is the leader and the second row is the follower. First row is the leader and the second row is the follower. So you can see that the cost is at least 1/3 compared to the non-optimal controller. You see? So there's more details in the paper, transactions on automatic control. So I think, I don't know, he has the internet in there. Let me see if I can. So that's too bad, I brought my. Copied, I thought maybe I'll do that. So if you type in huh? See, this is the paper. IEEE Transactions on Control System Technology 21 number 4 July 2013. Okay. So this paper, if you look at it, it talks about the leader follower, the dynamics of the robot, the non-autonomic constraint, and then you have the leader, the optimal controller. You see that with the G and all that. And then you have the leader stability, then you have the follower, kinematic controller, dynamic, and there is an obstacle avoidance here. You can see that. There is an obstacle avoidance. And this is the update law and everything. There's a flow chart. So this is the robot. You know, it has camera, but we didn't use it. And you see that the leader, this is the leader and this is the follower, and there is an obstacle there. And so there are two parts. One is the optimal controller, and this is the neural network stabilizing controller. And you can see that, you see those spikes in the tracking error. Do you know what those spikes are? What are those spikes? You see here, you can see even here also there's a little spike. When it encounters the obstacle, so it's going around it, it encounters the obstacle, and you see that the stabilizing controller has got more of an overshoot compared to the optimal controller. Okay, and you see there was a follower errors. Okay, and then here are the plots that I showed you. You see? Okay, so this one has more results, and there is some experiment hardware test bed, and so it's 8051 variant. The controller was 8051C programming and pulse width modulation. So it's 8051. Okay. Right. Right. Right, that's right, that's right. That's all you need. You don't need a whole lot. So there was another paper, yeah, it talks about number of neurons versus computational efficiency. So you really don't need a very highly computational, programming, So, but usually we do 2 layers for control. But this is a single layer, the basis function. So you can see that it talks about US digital quadrotor encoders for measuring, the velocity and all that, and then there's a reference velocity and all that. So it goes into some extent. Here is the update law, and so this is a hardware test bed, hardware results. So this paper was IEEE Transactions on Control System Technology, Volume 21, Number 4, July 2013. Okay, so this is implemented the optimal controller using 3 neural networks. One is an observer, 2 actor, and critic neural network. So when I bring my laptop, I can show you the videos. Okay. So any questions, guys? Any questions on the hardware? Like you said, I think you really don't need a very complicated in the engine control that I showed you. Originally, we thought that you need a very complex processor. And we went with I think it's Intel Pentium with a 900 megahertz crystal. And we found out, that's where we were doing some experiments. We increased the number of neurons from like 30 neurons to about 250 or 300. And we saw that there's, it jumps and after 80 neurons. But we didn't require 80 neurons in the hidden layer. So we were able to do a fraction of that computing power. When we were implementing, I showed you the engine control stuff on Saturday. So what it means is you really don't need a very complex processor for real-time control. That's what I mean. And we want to do online real-time learning, right? You can't, there are no targets. So when somebody asks you, why can't you use supervised learning? What is the answer? What is the answer? We have unknown dynamics, so? Right, there are no targets. Even if you know the dynamics are known, Even if you have dynamics unknown, you have to really do some work in order to find the targets. Because like x dot equal to f of x plus g of x times u, you really need a target for f, you really need a target for g. You see what I'm saying? And look at all the update laws. We don't use the targets, we are using what? What are we using to tune the weights? So what did we use to tune the weights? What does the observer or identifier uses to tune the weights? Huh? What does the identifier uses to tune the weights? Look at your slide. Look at your slides. Right, estimate f and g. So what is it using? Look at the slides. I give you a minute. So that shows nobody is reading. After going back, I did mention that multiple times. So can somebody answer my question? What do we use to tune the identifier? It has to be loud with the fans. And what do we use to tune the critique neural network? You take the Bellman error. Exactly. So what do we use to tune the critique actor network? That's critique. What do we use to tune the actor network? Control input error. Remember, you can't forget if somebody wakes you up in the middle of the night and says that, tell me about adaptive critique. You got to say that and say the critique neural network is tuned by the Bellman error and the actor neural network is tuned with the control input error. We spend a lot of time. Remember that? So there's a saying in Tamil, after hearing the Ramayana, and somebody asks you the question, how Rama and Sita are related? I don't know, maybe in your language you also have that. Same thing, you see. So this is the problem, you see, that's why I asked you. So what signal do we use to tune the identifier? Do you have an answer? I know you are answering for the active critique. So what signal do we use to tune the identifier of the observer? It has to be measured, right? It has to be measured, otherwise we can't do that. So what do we use for the identifier of the observer? You got the slide? Huh? You want me to put the slide? Okay guys, here. So here, this is the identifier. Here is the expected value. Okay. So look at that. I know you generate the history because you need the inverse. Then look at that. So here is the update law. Okay. So here is the update law for the identifier. So what am I using? So you see that zk minus alpha times that. So what am I using here? What is that? So that error is basically, in this case, this is the identification. So I'm measuring the state and estimating it. So it's basically the state. Okay. So for the identifier, you are measuring the state if you know that, right? If the observer, if you can measure, but if you can measure the state, you're also estimating in the case of an observer, because an observer you are estimating also the state, you're also estimating the dynamics. Then you have to use the output. The outputs are measured, you know there, so you are using the output error. Y equal to C times X hat, Y hat equal to, and Y equal to C times X, right? And you're using that error, so don't forget that. So this is very critical. So there is a difference. So if I'm using, let's see here, if I can go to a little better place.
Then you have to exit from there.
Oh, I have to exit from there, okay. All right. So if I'm using identifier, and in the identifier, I know the state. So, then what you do is you estimate the state, okay? So this x of k plus 1, you will see that this is f hat plus g hat times u. And here, x of k plus 1 equals to f of f plus g times u. So you basically taking this error, x minus x hat. For this is the identifier. Now if it is an observer, the observer doesn't have the state. You're also estimating the state. So basically what you're doing is you're estimating x hat and so here you y hat equal to c times x hat and y equal to c times x. So you measure this. So E equal to c times x minus c times x hat, c times x minus x hat. So basically this is the error in the estimation. So this is where the C inverse, pseudo inverse comes in, because C may not be a square matrix. Yeah. So then you write the dynamics in terms of E of k plus 1, everything, and then you do that. So this is a very critical thing. This is a very critical thing. Okay? Any questions here, guys? Any questions? Okay, so today we spent about 35 minutes. So I'm trying to go into another new lecture, lectures 9 and 10. So event sample distributed network control system. So first we won't look at the event sampling. Okay, so we're going to look at distributed network control systems. So remember when so far we were talking about network control systems, right? We looked at optimality, we used neural network, we used the dynamic programming, we were using the Bellman error, control input error, all that stuff we have done. And the main reason the dynamics are becoming unknown in this case is because of what we call network imperfections. Remember that? Because of network imperfections, the delays, packet losses, quantization, the dynamics become uncertain, and when they become uncertain, you really need to do adaptive. At the same time, we are using optimality. So it's called optimal adaptive control. Okay, make sense? So now we're going to look at something a little bit more generic. So there are cases where you have here multiple systems, they are sharing the same communication network. Look at that. So you have a controller, you have a plant, you have a sensor, and don't worry about this trigger for now. So they're all sharing the same network. So in a traditional event triggered control system, you have a network You see that there is a sensor, there is a trigger. The trigger closes the switch so that the information passes through the network. And this is to prevent the network becoming congested. Now remember, before the network becomes congested, what will happen, guys, in terms of delays and packet losses? What happens? Imagine you are driving in a highway, even in India. There are a lot of cars coming in. What will happen when you are driving? In terms of going to your destination, what happens? Delay will increase. Does that make sense? So when there is a congestion, before things really congested, delays will increase. Or let's assume that there is a construction going on one of the lanes. There's only one lane instead of 2 lanes. So the traffic gets backed up. And when things get backed up, the traffic gets slowed down, right? And so the delays increase. So when in a network, not only the delays will increase, remember I told you that the packets also get dropped. Why? Because you only have so many buffer on your computer and the one who is receiving it. So what will happen is the packets get queued up, and since the packets cannot be transmitted, they get overwritten in a protocol. They get overwritten. So that same thing as packets getting dropped. You see? Packets getting dropped. So whenever there is a communication network and a wireless network where the bandwidth is limited, then the delays will start increasing based on the number of what we call subsystems. As the number of subsystems increase, the delays will also increase accordingly because everybody is trying to access. Just like in a highway, right? You want to take a highway because people travel fast, but if everybody is using the highway, then there's a potential that there is a chance of congestion. Okay? Okay, so what happens is, you have multiple ways we can resolve this, okay? One way to resolve it is by what we call event triggering. Event triggering is only you transmit the state vector when you really need to transmit. Okay, and remember I said that's called performance-based sampling. So when the performance starts degrading and becoming unstable, then you close the switch and you transmit. Otherwise the system would run open loop. Okay, it runs open loop. So that's one way. The other way that we're going to start today is that you see that application layer here, this is basically a layered network. Network has so many layers. I don't know how many of you. Did anybody has taken a class on computer networks or communication networks? No. I think if you take a network, they'll show you this picture here. So this is like a layer. So there's a physical layer, there's a data link layer. You can see the physical layer. Physically it's connected by a cable. That like Ethernet cable that you see on the wall. Okay? There's a data link layer. Basically there's a scheduling happens. I'm going to talk about it today. Okay? There's a network layer, which is the IP protocol, Internet protocol, how to communicate, handshake. There's a transportation layer, TCP/IP. And there's an application layer where all our control methods are basically stored. So what happens is your controller, is in the application layer, whereas the actual network has a scheduling in the data link layer. And there should be some information from here should go to here, and from here it should go to here. And traditionally, it doesn't. Okay? So that's called cross-layer protocol design. It's a big deal. In about 10 years ago, it's a cross-layer design. So the computer science guys don't understand the electrical engineering. The electrical engineering guys don't understand, just like you guys don't take it. So remember I was telling you, that's the problem. Most jobs, most stuff, you really need an interdisciplinary. And this tag, I don't know whether you talk to your computer science friends. If you have a computer science friends, talk to them, they'll tell you, I'm working on this tag. Have you seen a video? People say that I'm a software developer, I'm working on a stack. This is a stack. Okay? So the network has so many different layers, and each layer is dedicated to do some specific job, just like in the campus, right? You have head of the department, you have a faculty, you have a dean, you have a registrar, and then you have the director, right? Each does something different. So same way, each layer here is doing a dedicated function. So one way to minimize the network delay and packet losses is to basically bring in the information from the data link layer. You see the data link layer here? So that data link layer can send some information to the application layer, and the application layer would send the value function. So I'm using the scheduling information as part of my minimization in the critique, and I'm taking the value function from the critique, I'm going to feed it into the scheduling protocol. It was never done before. We were the first ones to do. And by doing that, what you're doing is, you're actually changing the delays and packet losses. You understand that? So the first part of the presentation today, I won't use event triggering. Event triggering is a third way of cutting down number of cars entering into the highway. Now, I don't know in India, if you go to US and you go to any very big cities like Chicago, okay, I don't know if you have seen any movies or anything. You know, there are exits or entry points which goes into the highway. Before you enter, there's a signal light. You can't enter that highway without that signal light being green. See? You know why? Because they want to make sure that they want to allow the cars that were already on the highway to go through. So they don't want to create congestion. And then actually controls how many cars enter the highway. And the primary purpose was to reduce congestion. But congestion is the ultimate problem. Before congestion, what will increase? What will increase before congestion? I already answered the question. Before congestion in a highway, what will increase? Delay will increase, not time delay, it's delay. Delay will increase, right? Because as more traffic going through it, it takes longer because there will be, if you have more cars going through. So the delays will increase. So the issue is, you really want to control the delay before it starts increasing. And so far, if you look at whatever I covered until now, I really ignored the network. You understand that? I completely ignored the network. My focus has been on what? On controller. My focus has been on the controller, but we really didn't do the network. So if I was, my bachelor's was in electrical engineering. If I was thinking like you guys and say, I'm not going to do anything with the network, then nobody's going to fix this problem. Because the computer science guys don't have a clue about control. Yeah. So that's why most companies want interdisciplinary background. That's right. And it's going to change, guys. The curriculum in India probably will be changing because some of this has to happen in AA. So that's what I was saying, that you got to have some background in the networks. So we were the first ones to bring in how you could have a marriage between a computer science and a AA. That's what we are doing here. So you can see that. So how do we do that? Information from the data link layer is going to the application layer. The application layer will send information to the data link, and they are trying to do that. Okay, so you know what happens? So we have a back-off interval. So the wireless network protocol, even including the one on the automotive, the one in the current automotive vehicle is called CAN bus, controller area network bus. It uses a protocol 82.11 called CSMA-CD. You tell the folks, if you guys go back for lunch, you ask your computer science, do you guys have any computer science friends? You ask them, what is CSMA CD? You ask them, what does that mean? So CSMA CD means CSMA, carrier sense multiple access. Carrier sense. So there in that cable, I'm just sensing if somebody is already communicating. First, that's what I'm going to look at. So what do you do when you are coming to a highway? You watch and see if there's any cars going through. So that's what I'm looking at. Is there anybody already communicating? Carrier sense. Multiple access. That means multiple people can access that highway, right? There are multiple, not just for one person. / collision detection, CD. CD stands for collision detection. So naturally, if that packet enters that highway and there's a packet going through, what will happen? They will have a collision and they will back off. So what happens is this protocol uses the back off interval. So when it sees that somebody is already communicating, it backs off. Okay? So this is a big habit that even I don't have it. Remember in a group, even in the TV, I don't know how many of you watch some of those Times News and all, they will be asking people individually, what's your opinion, what's your opinion? You know what happens? Everybody keeps talking at the same time. This is only happens in India. You won't see that much in other Western countries.
Sir, I guess they are knowing, maybe at the beginning Reliance came with a handset.
Okay.
Which is integrated, you cannot remove that SIM.
Okay.
And exactly the CSMA CD was the protocol for the communication.
Okay.
But after that, it obsolete. It is not.
It's not. It's one of the older ones.
Yeah.
Older protocols. It still exists. It's a standard, right? IEEE standard. So basically, that is a good example. Everybody talks, nobody can hear, right? So the same thing in that carrier sense, because you have to watch and see if there's a communication going. If the other node transmits, then it collides and then both the nodes have to back off. The way you operate is the back off interval is random. Whenever there's a collision, both will back off, and when they back off, they did such that it's random back off. Both will never be able to transmit, and they back off at random times, for random duration. You understand that? So then the one with the smallest back off interval will actually try to access the network again, or the cable. So this is how it works. Okay? So the question is, how do we bring the controller performance into the data link? You will see that we brought that value function into this, and we want to maximize it. And then we take the back off intervals or some information from the data link layer, and we are feeding it as part of the minimizing that value function. So this is what we are doing. There's the equation with traffic. I don't have it on my slides on the show, but in the book it does explain it nicely. So this is how you are doing it. So that means you are taking information from the data link layer and feed it to the application layer where the controller is operating, and you're also adding an extra term to minimize. You remember that? And then you take the value function and you're feeding it back to the data link layer so that you want to maximize it. Why maximize? Because you want the network to carry the maximum traffic. You see? You want the network to carry the maximum traffic, and you want to maximize it. So you have a minimization problem in controller and a maximization problem in the scheduling layer. And this is how you are scheduling. So whenever there's a collision, you back off. And the back off is also adjusted based on this min-max method. So this way it generates the best approach, and it's called cross-layer design. The word cross-layer. You can ask those guys from computer science, they'll tell you what is a cross-layer design. Cross-layer means in the old systems, each of those layers on the right-hand side, they never communicated. But in 2000, when the networks are getting popular and cyber-physical systems are coming in, then people thought, no, it doesn't work like that, where people don't talk. So when two people don't talk, things don't happen, right? That's important. So whenever two people have a problem, what do they suggest? They say communication. Communication is the best way to solve it. It's not good to back off forever. So that's what happens. And that's important if you are married. You talk to your parents, will tell you. Always that issue. So the conflict, whenever there is a conflict, best is to talk and you want to back off immediately. Never go, you need to fight, right? You have to back off. And then you try to find a way to communicate. So communication is very important. So this way, the same idea in these protocols. Okay? So I'm going to, any questions here, guys? Any questions before we take a break? So I will talk about it, how to now we are looking at how do I bring that expertise. That's why I said cyber physical. So as a double E student, you just can't graduate without having that background. Pretty much every job requires that. That's why I said, if you in double E in IITs, Madras curriculum and all, they have a computer network course. You see? How about you guys? You guys have a course? Networks, that's important. That's important. See? That's the drawback when you go out. So that's very important to have the background. Networks, at least one course. And the programming, just like I said, there is also a lot of programming here. Any other questions, guys? Any other questions? But you understand the highway as an analogy, right? And it makes sense, right? Many times you are going to some other town, things get blocked up because there's a lot of traffic. Or when there's a festival, there'll be a lot more people. And so it's just a common sense. The same thing is happening here. What is your question? It's a maximize because you want to maximize the amount of traffic going into the network. Whereas in the control problem, it's a minimization. Remember I told you in the beginning, everybody wants to, in the reinforcement learning also, they try to maximize the reward in most computer science. They always look at everything maximum for them. So they want to maximize it. But in our case, we are trying to minimize it, the value function. That's the difference. Right. Error and also input. Right. You just take that same thing and go put it there. You have the code. You can look at it. You have the code. Remember, the code will be shared. You guys run it. And that's why I keep telling you, you really need to dig into the code and do that. Otherwise, you are not learning, right? You're not learning. And the other thing that, remember, all of you know, I want to give you this also. I was walking yesterday from my guest house through the gate. Okay? Through the gate, guys. I was really surprised. I thought that was a good one, a good quote. This is from General Patton, who is an American military general. Have anybody read the quote? This is on your campus. What does it say? I am positive you guys don't go through that gate because you guys drive car. You know what it says? For best performance, I'm just giving you the essence. Don't tell somebody how to do it. See? But tell them what to do. That's what I'm here for. I was about to say, I was searching for that. So now I'm very happy. So when we gave you the MATLAB code, it's like you guys were asking, no, like spoon feeding. Never do that. Nobody's going to do that when you go to the real world. So just think about it. So you were given, and we've been telling you what to do. That's all you need to pick it up. But we won't tell you how to do it. We just gave you some stuff. But you have the MATLAB code. Use the MATLAB code and take pieces and just look at it. What is done, how is done. Then you can say, okay, I can modify this. You see? Otherwise, you will never learn. Remember I told you the learning thing? You're learning for a grade, but you're not learning for yourself. That doesn't stop. So you'll forget. Let's say after one semester, you will forget everything. And that's what they want you to do when they come for the interview. They want you to ask you questions that you cannot forget. Think about it. Okay? All right, so that general pattern, if you guys have not seen it, I want you to walk from the guest house through that little gate there, and you see there are a lot of nice courts. There's a reason why they have it. I'm positive if I would have student, I would have just overlooked it. You saw that? Yeah. Yeah.
Throughout the campus, we can find
The general pattern American. I think that's the right thing, because as people from the top, they only tell you we need to do this, we need to do this. That's it. How to do it? People will down, they will decide. So the same thing, I can only show you things, but it's your job. How much you want to get out of it. Exactly. Okay? So I'm going to stop here. Okay, see, these are real life situations, and I've been giving you analogies. So keep this in mind. It happens in real life. So nothing we come out in research is something that is completely out of the blue. Everything happens what we do here. And any invention is very simple. Otherwise, there's something wrong. And there's another quote. I'm going to leave you this. Einstein. What is that? Is there somewhere there? I don't know which quote. Einstein has so many quotes. Okay? The quote that I know was, there's a quote that applies to me or anybody. So if I can't explain it simply, that means I don't understand it well enough. So I tell that quote to all my students who take my class. Yeah. So that's one thing. That means that if somebody, see, this is what happens also in interviews, right? They're asking you so you can explain it in a very simple manner. So if you can't explain it simply, that means you don't understand what's going on. So keep these, there's a reason why your campus have all these codes, because there's a real reason, yeah. All right, so we'll take a break, and then I'm going to show you how to do the cross-layer design today. And then, sorry that the video didn't work. I thought I forgot. That's why I usually have to bring my laptop. So, okay, any questions here, guys? So what we're going to do is we will see how to pass the information between the two layers, okay? So if you remember this, you guys probably can recognize this. So each pair or each system, or we call subsystem, you write the dynamics like this, which you have written, right? Now you see that L, the L is in the top. The L means the L subsystem. Because so far we have been looking at one subsystem, right? Only one. But now there are, let's say, there are so many different ones. Okay, so now you see that there is also an L in the dynamics. So you take that and then you basically continuous time and discretize it and do all the network imperfections. So you see that there's a L in the superscript. That L means it's basically the L subsystem. Got it? Because it's distributed. Okay? So you will have these matrices like you have seen, and you have AZK. You see that this has the packet losses and delays, and the BZK of the L subsystem has its own packet losses and delays. And they're all sharing the same network, right? Remember the same analogy. We have a highway, everybody shares the same, all the cars share the same highway. Okay? So now, if it's a linear system, therefore we are going to use the Q-learning. So here is the actually value function. It's a quadratic. We don't know pKl, and you have to solve the Riccati equation, stochastic Riccati equation, to obtain the pKl. Okay, and not only that, the Riccati equation also requires the system dynamics, AZK, BZK. So and it goes backward in time. So we are not going to use that approach, and the familiar approach is basically what we have covered in the class. Okay, the approach we covered in the class is writing this as a H matrix or a G matrix, whatever, and then you see that the H or G matrix has got all these AZK, BZK, and then you need the inversion of this term multiplied by that to estimate the Kalman gain, Kk, right? Remember that? And this is how we have been doing, and the benefit is it goes forward in time. You can implement it in real time, and this type of approach is called optimal adaptive control. So this part is not changed.
Sir, what is the WLC stands for?
Which W? Oh, wireless network control system. So wireless network control system. So wired or wireless? Okay. So very similar, and you see that here is the Bellman error or temporal difference error. You see that this is the Bellman error or the temporal difference error, and once you get that for each subsystem you have a Bellman error, and you construct the history and you try to come up with an update law 8.6, and you adjust those H matrix. And once you get the H matrix, then you can compute the optimal control input like here, which is very similar. And the only difference is, remember, you see there is a superscript, there is an L. So this L stands for Lth subsystem. Okay? So the Q-learning, if it's a linear system, you're running the Q-learning on all of these different subsystems. But then, normally we are not optimizing anything on the network parameters. We're going to do it. This is what we have done. Okay? So this is exactly the slide I'm basically talking about. You see the history, you derive the Bellman error, and you get the update law. All this stuff you have seen before, and here is the optimal control input. Basically, you state the theorem that if you have an Lth subsystem and you have an initial admissible control policy, the CPS, the cyber physical system, Lth pair, optimal control system, let the adaptive update law is given by 38. then there exists a learning parameter rate for the health subsystem such that the estimated parameter and optimal signal converges to the actual parameter and so that means rho hat converges to rho, U hat, the optimal control policy converges to the optimal policy of the health subsystem. You see that there's an L there. So you are only proving for each subsystem they do converge. Okay, but that's not what we want. We want some information from the link layer. So the link layer does the scheduling. Why? It uses this information and it has to access the network. It has to transmit information. You see? So in order to access the network, it has to follow a protocol. The protocol is CSMA/CD. Remember we said that. CSMA, carrier sense multiple access, /CD, collision detection. So you see that here in this slide, look at the way I modified the cost function. There are M pairs, there are totally M pairs. So I'm taking all the cost. Now typically we have a quadratic. Look at that. I added another term here. This RLK, beta times RL, beta L. So beta L times is the cost function. You see that? So JLK is the cost function for the health. RLK is the CPS average traffic payload during that interval 0 to KTS. And beta L is the weight of average traffic payload. So this beta J, RLK is the total traffic. Okay? So here I'm trying to minimize this. I want to minimize the traffic I need to send through the network. Okay? So you have two cases. This is a scheduling problem. One is health CPS has to be scheduled. The other case is health CPS has not been scheduled. So there are two cases. Because there are multiple subsystems, they're all trying to fight. Everybody wants to transmit in the network, right? So, but only one person can transmit. That's what the CSMA/CD protocol, drawback of the protocol. Only one of them can transmit at any given time. So when more than one tries to transmit, the packets collide and they back off. That's what we are doing here. So you see, look at that. I'm going to use a utility function for the scheduling. So the utility function is, you see, look at that. I am maximizing the pi for all the, for all of those thing and for all L, okay? So where delta J is basically the difference between two instances, two cases, okay? I'm trying to maximize it. And gamma K is a scheduling indicator. GK is a scheduling set. So what I'm trying to do is I'm trying to maximize it. Okay, that's my utility function in the link layer. I'm maximizing it. Whereas in the control layer, application layer, I want to minimize it. So I added a term to reduce the amount of traffic. That's why I was minimizing it. Here, I want to maximize it. You understand that? I want to maximize it because I can transmit often. So the way we do that is, you see the back off interval? The back off interval is a function of this maximum quantity. This maximum means minus of that is minimum. And then you have the NLK. NLK is the delta is the scaling factor. NLK is a random variable which satisfies the Gaussian distribution. So this back off interval, as part of the protocol, you're not changing the protocol. You're only changing how much you back off. So when two people are trying to access the media, you are trying to maximize that utility function such that the network is being utilized to a maximum. So always somebody is transmitting. That's the goal here. So let's think in analogy in the analogy, let's say in the highway, imagine, remember I told you at the entry points you have a signal? Imagine if the signal is always red, then nobody is going to go through the highway. The highway is empty. It's not being utilized. You see? So that's exactly what we are doing here. So you want to maximum utilize the highway so that there are a lot of traffic going through, but you also want to control the traffic that's entering through that. So there is a way to adjust the lights. That's exactly what we are trying to do. So when I say the light becoming green means that particular subsystem is going to transmit the feedback. You see? So here we are not doing any event triggered at this day today. Tomorrow we'll talk about event triggered. But so today we are not talking any changing the sampling interval. Here we are only talking about what information is needed from the application layer to the link layer, and what information is needed from the link layer to the application layer, and how to use this. So we are using a maximum problem in the link layer and a minimum problem in the application layer. This is how we are formulating the problem. Okay? Any questions here? And the way we are implementing it is by finding the back-off interval so that if somebody has a lot of data, he would transmit first. So that means in order for him to transmit, he should have more data to transmit. That's what it boils down to. So let's say that in what is the analogy in the network, like in a highway. So let's say that you have an entry point. At the entry point, there are a lot of cars backed up. They are the first ones to get access to the highway. You see what I'm trying to say? Why? Because there are a lot of cars waiting for a long time. You see? So think about a highway where you have multiple entry points, and one of the entries, let's say there is a Kumbh Mela or whatever festival happening, there are a lot of cars waiting to get onto the highway, whereas in the other entry points there are not that many cars, right? Because if there is a backup, that means in that particular entry, people are waiting for a long time. That's the delay will increase. So you give preference to those guys coming in. So that is what we are trying to do. We are maximizing those that really need to transmit. And that's how it's incorporated. How is this incorporated? As part of the back-off interval. So that means that particular subsystem would have a smallest back-off interval. So it's going to go first onto the network, and then it's going to transmit. You see, that's a very simple idea. But when there is a collision, that means someone else tries to sense the network, there will be a collision. Then both will back off, but the one that is going to back off smallest is the one that's going to transmit, because you want to reduce the amount of delay. You understand that? So the delay is proportional to the back off interval. The longer you back off, the longer is the delay. You understand that? Longer is the delay. Right? Because he's backed off. He's not able to get onto the highway. Okay? So longer is the delay. So that's how we basically modified that. The utility function. Okay?
Sir, if you consider that there are two subsystems,
Right?
and both of them have same amount of data.
Right. So if they have both same amount of data, it's possible that you have this scaling, you remember the learning rates, there will be some difference. So you don't pick exactly same values for all of them. There's always going to be some difference. So that even though the rest of it is the same, the scaling factor or this zeta, you see that the scaling factor here, the zeta may be slightly different. So one will be accessing that network earlier than the other. Okay?
Sir, is there any priority option of subsystem?
Is there any what?
Priority option?
You can also include that. You can also include, say, let's say somebody got to like a Modi ji or someone like a VIP coming in. Well, you basically give preference, right? So if you are giving priority, you can also enter that. Yeah. But the way you enter that is through that back-off interval. That means that they don't back off longer. They basically will have access to the network much faster, or the highway. You see? Got it? Okay, so here is we'll see this in the next slide. this blown up on this algorithm. So algorithm 8.1 and 2 represent the proposed optimal design. 8.1 shows the value function. So basically here is the picture. Look at that. BI stands for back off. This type of shaded one, you can see that CPS pair obtains wireless channel to transmit data. So it's accessing the channel. But if there is a collision or if somebody is already transmitting, then you back off. Then you try again transmit. So this kind of thing goes on. And you see the first CPS pair, second CPS pair. So you will see that mth CPS pair. So they always have kind of a, like a shifted. And you see that this type of thing means CPS pair waits while wireless channel to be free. So if you look at this guy is transmitting. So this guy and this guy has to wait. Because only one can transmit. Got it? Only one can transmit. So that's what you're adjusting. And once you adjust it, then it goes. So this basically shows that given the multiple CPS pair optimal control, select the CPS pair with highest utility. See that? Highest utility. So the highest utility, that is the lowest or the shortest back-off interval. When you have the highest utility, it is the shortest back-off. So everybody will back off, and the one that has the about to have more data will have the shortest back-off, and then he's going to transmit first. Highest priority to access the shared communication network. In addition, the proposed algorithm can render the best performance schedules for every CPS pair. So we have to show that if you have 10 of them, everybody can be transmitting and they are able to maintain. And we also have to show that the network is not always free. Because like as I said, if the highway is, because of this, our bad method, if the highway is, nobody is traveling, then it's a bad thing. We have to utilize the highway up to 99%. And we are going to see that. So let's look at the algorithm 8.1. So you can see this is mainly for the controller. So here you are estimating the h hat is equal to 0. Calculate the value function estimation error, which is the Bellman error. Then you update the parameters h hat. Then control input, calculate the control input matrix using h. Then you computing the Kalman gain for each of the systems, and you keep doing that. So you do that for all of them, and you increment the time. So algorithm 8.1 is basically for the optimal control policy. In 8.2, so here you are initializing all the wireless network control system states, while you are between the slowest time to the next time, implement the control inputs from the controller. If multiple control inputs have been received at the system on the same time, then apply the most recent control input to the system and discard all other control inputs. Now, why are we receiving multiple control inputs? Remember, we talked about the protocol, TCP/IP. It's possible that multiple of them can travel different routes, and it's possible that multiple of them would come, and you pick the most recent one based on the time, and then you transmit that and you ignore the rest of them. If old control input is received or arrived after the new control input being received, then discard the old control input and apply the new control input to the system. Else the control input is received by the plant at different time and kept in order. So basically what happens is none of them arrive, then you keep the same one that you already have from the last time instant. Then once you have received it, each subsystem receiving it based on this logic, then you apply all of them. And then once you apply, then all of them will try to access the network for transmission. And then you need to go to 8.3. So what does the 8.3 distributed cross layer? You see that it's called cross layer design, scheduling design. So here you are initializing the beta naught. And each wireless broadcasts its utility function. You see that that's the utility function. So it tries to broadcast. Everybody says that I have this priority. have this priority. They broadcast in the network, okay? And then everybody receives that information, and that information is a function of the value function. Look at that, the value function from the control. Then as the time, you determine the back-off interval because there are more than one that wants to transmit. And the one that has the highest utility function has the shortest back-off interval will be the one will be given to enter that network, or it will be. So you're contending the wireless source, then the smallest VI then transmits first. And then this is how you're scheduling it. Okay, then it broadcasts the message to notify all the users that once it's completed, it broadcasts the wireless channel is free, so then it goes off. Then other ones will try again accessing it. You understand that? So this is how the protocol works once you compute the control input. And then these two keep going back and forth. Okay, any questions here, guys? Any questions here? So there is optimal policy, and you look at it here, the utility function. The utility function uses the value function here. You see that? It uses the value function. And the goal is to maximize their difference. So you want to convert, so the negative sign. So that's what you're doing. You're trying to maximize it. Any questions, guys? Any questions here? I want you to read this after today's class. And then, remember, if you don't read it, you probably will go, tomorrow if you come, it will look very new. So how many of you are spending time every day? I see only 3 people, all the students probably are not doing it. And some of them are not coming. I think I see that names. Maybe they have other things going on. Yeah. Okay, guys. So now, still not done yet, looks like. So basically, it notifies the other user. Then you see that then it updates the entire wireless network with the utility function. And then you try to balance it. Wait for the wireless channel to be free, and then you update the timestamp and also the back-off interval. And then you update again. So what happens is this keeps going on. You're updating the utility function, you're updating whether the channel is free, then again you schedule all the players, and one of them only transmits. Once it transmits and it's done, then basically it sends out a message to the network saying that I'm done, someone else can use it. Now in a highway, what happens is, let's say the car exits. As the car exits, there's another light, and it exits, it senses it and transmits to others, knowing that the car is exited the highway. Okay?
So what is the timestamp?
Timestamp is basically each of the packet has a timestamp, and also remember the network has to have the same time, global time T. Global time T, right? The network has to have some time. So this time is same as the sampling interval in the control. And they both have to do this at the same time, okay? And TS, you see that the TS is a sampling interval. K plus 1, K plus 2. K equal to K plus 1, that is basically the new one, okay? So there is also called fairness in networks. Fairness is an important factor in scheduling. So what is fairness? So imagine that you probably might have seen it. Somebody always get a priority, right? Let's say you're waiting to enter a highway. And nowadays, a lot of people, we might have seen this because, like a movie theater or a temple, you are entering a temple. How do they give priority in a temple? Huh? One is passes, but there's other way they do now. Donation or pay, like there's a ticket. You have different, if you go to Tirupati temple or something, they have a different pay. Somebody they have a general category, you don't need, only you get a ticket so that you can go. It's free. Then somebody who want to wait for 5-6 hours, they get 200 rupees or something. Somebody who really want to get, you pay 1,000 rupees or something and you get a golden ticket, whatever. So that guy doesn't stay too much. So what they do is at the entry point, they will let anybody waiting with the 1,000 rupee ticket, they'll say, oh, go. And he'll goes first, right? And the other group and the free ticket guys wait forever. So, but then there is a called fairness. This is a big deal in networks. Fairness means it's unfair. If you are entering everybody, that's what they do. But everybody entering with these tickets who are paying more, but then the guy who was poor probably would be standing there forever. Right? So how do you measure something is fair? It's not fair, right? The word fair. So there is a criteria called fair. It's called fairness index. So that means that they want to make sure that index is high for everyone or equal. You see, because somebody is getting through some, free tickets. So the way they do it is in most temples, when you have one person or two people going with the 1,000 rupees, there's one person going at 200. Okay, and there's a 0. But then what happens is when there's nobody in the highest paying, then you let the guys with the free tickets, they let them go fast. So there is a way that they adjust the number of people going in. Okay, so the same thing here. So we want to, in network scheduling, it's a bigger deal. We have to ensure that all the users are treated fairly. Why did this problem occur? Because a lot of them are, a lot of processors are accessing memory. A lot of users are accessing shared resource. But if you imagine, if you have a network and you are sending an email, and the email takes 4 days to reach, whereas someone else like me takes 1 day. It becomes unfair. So that fairness is a way to make sure that everybody gets through. You see? And the fairness index is a big deal in computer networks. So there you see that important factor. A fairness index is defined as, you see that RI, the waiting factor, the traffic load. So if you have more traffic, then you should be given more opportunity to access the network. You see what I'm trying to say? So if you have more traffic, you should be given opportunity to access the network. Unless you access it, you will not be able to transmit those information you want to communicate. So that's how we basically try to find a way to check the fairness index, okay? And we basically do that and, and then try to compare it, whether everybody has been treated equally or close enough, close equally, okay? So let's see whether it works. So we start with our very popular example. So this example is what? Can somebody tell me? Batch reactor, that's right. So this is a batch reactor, inherently unstable system. Got it? And so you have the batch reactor, and B is not a vector, it's a matrix, non-square matrix. So we are going to check the proposed stochastic optimal control in figures. So the page limitation, the book doesn't have all the details, but look at the papers. There's a lot of papers that have more details. So look at that. So you're able to control, basing the optimal control, the Bellman error converges, the control policy converges. We know this because we have done that, right? Now look at that. Look at the network latency. You see that there are 10. We have 10 pairs. And look at that. The traffic delay increases, then it transmits, the delay goes to 0 or comes down, and then the delay picks up again, and then it transmits again. So these are 10, 1, 2, 3, 4, 5, and so forth. So it transmits, the delay increases, then it transmits. Whenever it transmits, what will happen to the delay? It goes down. So this MATLAB code is there, and I'm positive Professor Bera would share it with you. Take a look at it. So this has the optimal controller and the scheduling algorithm combined. You can run them together. Okay? So whereas when the one that transmits, you see as we talked about it, the one that is waiting, unscheduled wireless pairs have to wait, the wireless network latencies increase. So that's why you see that this guy is not transmitting, it's increasing. And it's given a chance here, then it transmits. The third one gets a chance here, and it transmits, while the others are waiting. And the fourth one gets a chance here, it waits, and the other one not transmitting. Now, so wireless network latencies increase based on the BI values, the back-off interval. So what we do here is the utility function. Look at that. The proposed method essentially has the maximum utility. And after some time, as the number of we compared with other methods that are very popular. One is called greedy scheduling. Greedy scheduling means the ones with the maximum one will ultimate transmit. We also have embedded round robin. Round robin is if there are 10 people, you go first, you go second. You know what I mean? So one at a time, you already assign that, and then you are transmitting. So what happens is, as the number of users increase, you see that how the utility drops because they can handle it. The network delay increases, and that causes problems. And then the other one is the greedy scheduling. Greedy also fails, whereas our approach maintains the maximum utility value. Now look at this fairness index. So what happens typically is, when one of these approaches have maximum utility and you keep transmitting, but it doesn't become fair. A lot of times it becomes unfair. So to check the fairness, we did that, and look at that. In this case, embedded round robin is very high fairness. Next, the blue, our approach is very close to the round robin. And look at the one that has a very low fairness index is the greedy scheduling. Now, why is that greedy scheduling has the lowest fairness index? Why? And why is the round robin has the highest fairness index?
In round robin, everyone is like number.
Exactly. It doesn't matter how much he has information. You don't have any higher priority. Everybody gets equal priority. So therefore, everybody is equal. That's why it is highest. In a greedy scheduling, why is it low?
Because everyone has
Doesn't get to transmit. Yeah, it doesn't matter how much you have the data. You don't, you don't transmit. So somebody is telling you, you got to wait. In the temple case, the poor guy waits for 7 hours. That's what that is. Whereas in the proposed approach, you are taking that information and you are basically using a very calculated thing. Therefore, you see that it's still high enough, like 99 something, but it's not as high as the round robin. You see that? At the same time, the performance here, you see that on this plot, we're able to show that the performance is better than the others. So that's because you're communicating between the link layer and the application layer. They're constantly chatting. You see? So this is very important. Now, why is this important? Because, remember you saw in the previous example, so if you have a protocol, you tend to wait longer. And if you don't use the proper scheduling method, this guy waits forever. This guy waits forever. And that increases the network delay and packet losses. The system will become unstable because it's running open loop. Remember that? It becomes unstable. So that's why you have to have a communication and take information from the link layer to the application layer. All of us as engineering people, we write code in the application layer. The computer science guys write in the other layers. Many times they don't talk to each other. That's the problem. Okay? You see? They don't talk to each other. Okay, so it says here a little bit, a third, the utility function with different scheduling schemes. The proposed cross-layer scheme maintains a high value of utility, and the other one, round robin and greedy, are much less than the proposed scheduling. You read that, it gives you, and eventually the fairness of different methods have been compared. The fairness indices shows that the proposed method is reasonable, compared to the others. Okay? So tomorrow, I'm going to stop here. I'm going to start 10 to take. So tomorrow we're going to look at the event triggered. So event triggered is, once you do this scheduling, I want to design a triggering mechanism to transmit those packets. That's another additional new thing that came out in 2009. That, remember I said the way you sample the closed loop system, and typically the sampling interval is what? In the previous TS is a constant. The sampling interval is a constant. But that doesn't work when you are bringing the network. So now what we're going to do is we're going to alter that, and we're going to stretch if somebody doesn't have to transmit, he can wait, we can stretch the sampling interval. Otherwise what will happen is that particular node will have more data to transmit, and even though you're doing scheduling, it may not be enough. So there is a new method called event triggering. Okay? How many of you heard that? Event triggering. So why? Did you guys, are you working on the event triggering? So who do you work with? Huh? You need to talk louder. Professor who? Huh? Oh, so he's doing event triggering. So event triggering, we're going to talk about that. Yeah. Okay? So tomorrow, again, all this is very brief. There's a lot of papers have been published in there. We're going to talk about it. So in event triggering, it's like a signal light. There's a switch. And you basically, you stretch it, you keep it in open loop. And when you're about to become unstable, then basically the switch, that would give you remember in our case, it increases utility. And the backoff interval will be shorter, and then you transmit. That's how you do it, and we're going to talk about that. Okay? So we're going to talk about that in the tomorrow, first thing tomorrow. Okay? So I want you to check this part of the code. This is chapter 9. I want you to look at this. This is chapter 9. There's no event triggering. But eventually we're going to get into event triggering. Okay? Now, I can give you a little background. Event triggering, we have 5 minutes. So I'm going to discard this. Now, if you remember, intro to NCS. If you remember this intro to NCS, you keep going back. This is event triggering background. So you can see that here, so you have the network, you have a sensor that's willing to transmit, but then there is a switch which is controlled decided by either the time-based or event-based. Time-based is every 5 seconds, periodically. Event-based means you basically look at some performance. In this case, you're looking at it whether the system is going to become unstable. Then the one that's going to become unstable first will get the priority to transmit the data, and it closes and goes out. So you sample the system states, then the decision is how frequently to sample the plan, then and how frequently you transmit. So in a classification, you have the time triggered, which is periodic. You can also do event triggered, which is based on which one goes. So in a time triggered, you see this signal is periodic. You're transmitting every periodically, which is given by TS, a fixed sampling interval. Look at the event triggered. Event triggered, this duration changes based on stability. You see that duration changes. So this duration changes. Main advantage, reduces the communication traffic and saves the network resources compared to time triggered. So that's the main reason, because you don't need to transmit a lot of packets, from the sensor. You can do that. Main drawback, what is the drawback? Inaccurate trigger condition might cause the system unstable. So if you don't decide when to switch and when to transmit, you're running in open loop, And if you are not able to transmit, your system will become unstable, because if you don't decide, that guy will get the preference. So how does it work? This is what we're going to use it. There are different ways you do that. One of them is zero order roll. So you have a trigger. You see that this is a discrete time system. X of k plus 1 is a times x of k. So you have a trigger. You compute the error, 0 volt. So current value of the state minus the previous value of the state at the previous time instant. You are comparing this time, and that is computed as the measurement error. So what you do is, your last transmitted value is xi. The current value is xk. You are measuring the error. That error keeps increasing because you are not transmitting. And if the error increases to some value, and you know that's going to cause instability, then immediately you transmit. And the error becomes 0. So that's basically, how do you determine that condition? So here is the control input design in the event triggering. So is uk equal to k times xk when the event is initiated? That means the switch closes. Otherwise, you're holding that based on the previous value of the control input. Okay, previous state. So then the closed loop error, measurement error, is given by this equation. Here you know A and B. You can analyze the stability of the system. So the error becomes 0 when you transmit. Otherwise it does become 0 when the event is not initiated. And K is the stabilizing gain, given A and B. So people have designed this, and they want to make sure that this system doesn't become unstable by designing a condition. Now, how do you design a condition? That condition is given by this equation, which is I showed you. When the event trigger error is less than or equal to this, a function of the state, okay, the event should be triggered. So if this condition is violated, then immediately the switch closes, the event trigger error becomes 0. That transmits, that particular node transmits, need to transmit. So that error is tied to this distributed scheduling. Understand that? That error is tied to the distributed scheduling. How do I get this theorem? Through the Lyapunov. So we'll talk about that.
So this particular thing will be available in book.
There is some available in the book. If you need more details, you have to look at the event triggered control book. There's a new book that has come out last year, okay, and it also has MATLAB code. It's come out. It only talks about event trigger control, and that has come out last year. And you can look at it in this current book. There is some information in that event triggering, and I'll cover it in the next tomorrow, but not a whole lot. Okay. Any questions, guys? Any questions here? That's why this slide deck is called intro. Remember that? It's an intro. It's not giving you everything, you know. Any questions, guys? So we are a little past 12. So I want to ask you any questions. So remember, don't forget today, what time is the afternoon session starts? 3 p.m. So be here around 3, and we'll start at 3:50. Okay? And I think don't waste your time. What I mean is that means you can enjoy. You may want to use those code that was provided, run that. Remember that? Use the time to get your homework done and all that. And today's tutorial is the third one, right? And we will have the final one on the Wednesday. Tomorrow you don't have anything. And day after tomorrow is the last one. And when is the assessment? Thursday morning is the assessment, and the Thursday afternoon you will get the grades. And okay, so I use the time, run the MATLAB code, and I already gave you the code from general pattern. He can only teach you how to do it, what to do. We won't be able to teach you how to do it. You guys have to figure it out from the code. Okay? Any final questions, guys, before we break for lunch? Right, this is only zero order hold. So I won't use first order hold. We are going to go into what we call adaptive. And we won't cover in this course. If you use the other course, event triggered control, there we'll talk about it. Yeah. Okay? Any other questions? I know if you have taken a digital control class, we talk about zero order hold, first order hold, higher order hold, the same thing, Okay? Any other questions, guys? Any other questions? Yeah.
Sir, in the control design of event delay, whenever the event is triggered,
So the state is communicated to the controller. Then the control input is updated. You see what I'm saying? The control input is updated based on that equation u equal to kk times xk. Then that control input is transmitted to the actuator. All the three things will happen.
Sir, when the event is not triggered,
Right. When the event is not triggered, the zero order hold maintains the same control input as that of the previous value.
so what if we do not apply any control?
Yeah, I know. You were not there on the first day I talked about it. Now, if you don't apply any input at all, remember I said two ways. One is use the previous value of that. Other one is to make the control input go to zero. I know, I mentioned this in the first day. What is the drawback if you don't apply any control input or you make the control input equal to zero? What is the drawback? What is the drawback? People don't do that. Because what will happen is if you drive the control input equal to zero, the system will run open loop and the system can become unstable. So they use the previous value of the control input under the assumption that input to state stable. Remember that assumption I talked about? Input to state stable. So that input will maintain the system at least stable till you get a new control input. So this is the difference between driving the control input to zero versus maintaining the previous control input. Got it? Okay, what else? So all this stuff has come in the last 10 years. Now it's old now. So when we do not on Thursday, on Wednesday, because Thursday there's no lecture. Wednesday I'm going to talk about future path. How many of you heard of Industry 5.0? I'm going to bring my laptop on Wednesday. So tomorrow I'm not going to play the video. So maybe I'll bring it on Wednesday and then I'll play the video. So how many of you have seen a video of Industry 4.0? How many? Well, let me rephrase it. How many of you heard of Industry 4.0? I think you guys need to. Yeah, I think I'll show you then. I think it's important because some of you don't even know. Guys, you need to get your act together right now. Don't graduate. You'll be in trouble. Everybody's looking at Industry 4.0. So I'll play a video. I need to bring my laptop. You're far behind. Okay? All right. We'll talk about it.
Okay, another small thing I want to tell you that
So this is the assignment 3 what I have said, and this is with the nonlinear system. And can you see the structure of C matrix here? So why the C matrix is like this? Can you correlate with the discussion? Okay, let me see the that slides also, so that a little bit you can correlate the slide with the slide. Okay. So this is the slide we are talking about, optimal control of unknown nonlinear NCS using neurodynamic programming, finite and infinite horizon. Okay. So if you have this nonlinear plant in equation number 1, then you have to find out the original nonlinear plant, then the nonlinear NCS representation you have to find out. Means with the delay and packet loss, like linear system, what we did that AZK and BZK we have found out. Similarly, also you have to find out the nonlinear system representation using the network imperfections like delay and packet losses. Okay, fine. Then you see that we can do it by two ways, as Sat said. You see the ZK, which is defined using the state and the previous inputs UK minus 1, UK minus B, and also you can do with the that is by output of the system, that is Y of K0, where the output and all the previous inputs are there, and then you have to find out the augmented system representation, which is represented by equation number 2. And here you can see that very important what I am asking you, that to see the structure of the C matrix, where you see that when C matrix is invertible, okay, so the C matrix must be invertible, the NCS model can be represented using the input-output data, which is represented by equation number 3. Okay. These are the steps you need to follow, and then rest of the things like linear system, what you did, that the stochastic cost function has been defined, fine, then the stochastic cost function using input-output form is also here defined in equation number 4. Okay. Then the value function, then the HGP equation. This is for the finite horizon optimal control. This discussion already it has been made. Just I am showing you so that you can once again you can recollect it. That what we are going to be talking about. So this is the critique NN weight update, the actor design and corresponding NN update law, and this is the flowchart ultimately. for finite horizon stochastic optimal control. So here at least you will have the idea of overall control system. So here basically in slide it has been given for a folding manipulator system, but in your assignment for a lower dimension of system it has been given and corresponding the MATLAB code is also provided. So that you need to see that how it is performing for different cases. So what is your that is figure 6.7? That is the state regulation errors by using NN feedback linearizing controller with network imperfections. So in this case you are finding that error are growing. Okay, so that is also there in case of that particular system which is given in the assignment. Okay. So that you do first, just to run that one. Okay, and you see that what are the plots are coming, and then you see that what are the inbuilt functions are, means that subroutines are defined there, and try to understand at least with the block diagram or the flow chart, the things are going accordingly or not. That's all. This much only you do, that is more than enough. Then when you will get time, you will, more details you will look into the problem. Only two problems are there.
Code is given for problem number 1 and then the model is taken.
Huh?
The code model is taken is for the problem number 1.
Yes, yes. You will find that not for the robotic manipulator, it is for this system only. Okay, for this system only. One is for finite horizon, another for infinite horizon. Same system, one is for finite, first problem is the finite horizon optimal control, and this problem 2 is for your infinite horizon optimal control. But the system is kept same. So you just see that particular programming and you see that how it is working.
The dimensions should not be a problem. Because if you look at tuning robot, it's very similar dimension, so there shouldn't be any change in the dimension.
Yes, but here the B matrix dimension is different from the robot dynamics.
Because there it's 2 by 2, here it's 1 by 1.
So then actually lot of changes they have to do. I saw. And in programming, if it is the single input case, then it is much simpler. But if it is a BMOS, means at least multi-input is there, then need to be changed rigorously. Because many steps are there where you need to change for the different dimension. Little bit involved work is there, they have to do for the change in dimension.
That's why they have to understand the code, what it's doing, then only you can make that change. Unless you do the change, you won't get that, how to write the MATLAB. Yeah. I don't know, have you guys, any of you have written this much MATLAB code? Huh? You have written, but no other. See, I think in real life, he works for industry. You got to write That's what I'm saying. That's a realistic example. So he works for industry. Yeah.
So this programming, you try to understand that for actor what is the error, for critic what is the error, and how these errors are calculated here. At least this much you understand. Today morning only sir told that what is the error for the critic, what is the error is utilized for the actor. So whether that errors you can identify in the programming or not. That errors are calculated. You see?
No, even though the G is matrix is different, it shouldn't affect here.
Okay, they can try.
You know why? You know why? Why is that G dimension shouldn't be a major issue?
G is related to input U.
It's input U and G is usually the input U. How does the G appear? How does the G appear? You remember half R inverse G transpose. So rather than, you don't have to take the inverse of G and all. So G transpose for a vector is pretty straightforward. You remember that. So that's why. It shouldn't make it very difficult. The only thing is when you are, even in the system dynamics, it shouldn't be that hard. Remember the system dynamics, you have to get the new state vector. You have to call the routine and you need to get the state vector, right? So there also should be. So it should be very difficult.
Now some steps are there, they are actually for plotting or these things, their calculation is there. That's for that calculation, they need to change the dimension. Otherwise, as you say. Sir, if you once again, if you tell that why in this case the proposed one we have in the middle, the cost, but in case of NN-based feedback generation, why the cost is higher?
So okay, let me ask you this question to you. I did mention that, but let me ask you why in the case of feedback linearization, the cost is higher. You understand what feedback linearization, right? So if you have x of k plus 1 equal to f of x of k plus g times u, you are taking the u equal to 1 over g minus f plus v, right? That's the feedback linearization. So what is feedback linearization? You are trying to cancel the nonlinearity is through feedback. Now it's different from Jacobian linearization. What is Jacobian linearization? That's the Taylor series expansion. Remember, you find an operating point and then you expand, right? That's how you get the A and B matrices. But this one is feedback linearization, so you're still doing cancelling it, and then you still get a linear system. That's how you do it. So feedback linearization doesn't have any optimality. There's no optimality, number one. Number two, you need to know precisely the dynamics. So feedback linearization is a controller which is non-optimal. Okay? So as a result, the cost is higher because you have a gain within that. Once you get a linear system, you have to use a linear control, and you can pick your controller gain whatever you want, right? You know? Yeah. Okay. That's right. That's right. So that's one thing. Now, if you look at why neural network NDV-based offline optimal controller is always lowest. Why is it lowest? This also I said. That is correct. So remember, we talked about this. So when you are finding that function, you're holding the time, like it's not practical, but that's how you do it in numerical analysis or in finite element. You hold the time, and then you are doing it more number of iterations. So what it does by doing iterations, you're really driving the error close to zero at every point in time, you see? So since you're doing that, but that's how the numerical methods work, right? So you'll keep constantly iterating it and you're driving it. So at each and every point, the value function, which is a solution to the SJV equation, would be optimal because you're driving it till it reaches a. Whereas in the proposed approach, you're only doing once. Today morning I talked about hybrid, remember that? Hybrid basically does a few iterations. You see? So it's a little better than this, the proposed approach, because there you're doing a few iterations, not a whole lot. But whereas in the offline, you basically can do, assuming that you can do as many iterations as you want, till it converges. Since you're doing it at every instant of time, V hat becomes V star. And therefore that's the best solution you can get. That's why it is the lowest. You see? So V hat will become V star at every, and therefore U hat will become U star because you're using partial V star over partial. Remember that in the control input calculation. That's exactly why. You see? So that's why you have three plots. They're different, yeah. Okay? I think that's good that she's going to at least one. And there are three. So at least I'm happy. And you should get the similar result. When you change the system, you should get, unless you really tune that feedback linearization gain, and you try to lower it. You know what I mean? Yeah.
So for the next problem, the infinite horizon, you will find that this is the, in slide, the system is already given, okay, the same system we are taking, this system, and here you can find out f and g, how it is calculated. After introducing the delay and packet losses and the parameters what it is selected, it is in the slide, and this results at, because in slide, when you will run MATLAB program only you can see the figures, but what is that figure, what is the analysis, that you can do it from the slide here. So you see that it has been shown that what is the drawback of heuristic dynamic programming, that is value iteration algorithm. So if you do not take the enough number of iterations, then it may diverge. Okay. Then the effects of delay and packet losses, that is shown that that error may diverge, but in case of the proposed controller, you will find that the regulation error is converging. Okay. So with this analysis, you just compare the result what you are going to get by running the MATLAB program. Okay. And this is a summary you can use to understand that particular programming. Okay, so I'm closing here, but you just see the things, okay? very minor equipment, purchasing books, software, these things only. But they are not allowed to purchase computers and use. This is ministry direction. And only the computer and the laptop can be purchased through the branch. Because if there is a not writing a proposal, then you will not have any updates of the even they the same thing. They the only thing they do is they update your office computer once in let's say 4 years. So because the 4 years things go, and then they have a contract. It's in the buy. They have a 4-year maintenance contract. They will take it and they'll take it. They'll give you a newer one. You only allow one year laptop, or so you can choose between. That's the desktop. So and that's it. And that's not because you're teaching course. You need something. Then actually what happened is COVID time. COVID time institute purchased laptop from which because we are teaching more. Ministry guidelines are there. So in that every faculty member, but I am actually in a dark region. What happened? I was in Silchar. At that time COVID was there. So I got that college. When I am leaving, I have to submit it to the when I came here, you don't have money there. That's why I was asking because in that term is because they are not to the restricted whatever you want to purchase. I think that's the same thing. You get that.